Hello, my name is Luke and welcome to this Pytorch tutorial series. In this video, we're going through data augmentations and learning rates. As always, all of the code for this series can be found on my GitHub repo. A link will be in the description. So we're now up to section 6. This is the first video in section 6 where we're looking at training techniques for convolutional classifiers to improve performance. In the previous section, we looked at transfer learning, where we take a pre-trained model and we use that as a starting point for our training of our convolutional classifier, or could be some other network as well. What we're going to look at in this section is what do you do if the pre-trained weights, or you don't have any pre-trained weights, or the pre-trained weights that you might have for a certain model might come from a model that was trained on a very different data set to the one you have, and maybe aren't very applicable. I gave examples in the previous video of, say, you have a data set of image x-rays, CT scans, something like that, that are very different to, say, the ImageNet data. And so maybe the pre-trained weights in that case won't help you very much, but you still want to get a good accuracy, and maybe you don't have enough data to get there quite on your own with just the data you have. So in this video, we're just going to look at some very basic techniques of data augmentation, and we're also going to have a look at some learning rate schedulers, changing the learning rate during training. So the code I've got in front of me now is very similar to the code in the transfer learning notebook. There's only a few changes that I've made. So the first one is the addition of some data augmentations within our transforms, a composition of transforms. So previously we just had resizing the image to a fixed size, casting that as a tensor, and then normalizing it, right? I wouldn't really call these data augmentations, they're more just pre-processing steps. But we're going to have a look at some data augmentation techniques, such as rotation, horizontal flip, and we're also going to have a look at Pytorch's auto augment as well, an automatic augmentation technique that they've developed. So Pytorch transforms and Pytorch data augmentation. So why do we use data augmentation, or what is data augmentation? So data augmentation is a way of taking what limited data you have, or maybe you don't have limited data, maybe you have a lot of data and still want to do data augmentation, that's fine. And you're basically augmenting it, doing some sort of change to that data so that the content of the picture still remains the same, but the actual pixel values in the specific locations of the image are different, right? So we talked about how overfitting is where your model essentially memorizes the input, right? It identifies the exact pixel locations of all the pixels in your image and memorizes that point more or less exactly. So what we do with data augmentation is we add some little perturbations and changes to our image so that memorization is harder. We can have a look at some illustrations of data augmentations in Pytorch's documentation. So things like padding, you can zoom out and pad, randomly resizing and cropping your image, center cropping from a larger image. You could convert from a color to a grayscale image. You could jitter or change randomly the brightness, the contrast, and the hue and saturation with color jittering. You could randomly blur. You can do more complicated things like random perspective, where you're taking your flat 2D image and kind of rotating it and around and translating it in the third dimension, which is a bit different to just rotating the image or doing a random affine transformation where you're rotating, sort of warping and skewing and moving the image around. Random perspective, you're kind of moving into the third dimension there. So in all these techniques, you can see that the content of the image is the same, right? It's still the same information in the image, but we're sort of representing it in a bit of a different way. It's very easy to sort of see what I'm talking about in the image domain. Different domains for different data types, it might be a bit harder to work out what a data augmentation would be, but maybe you've got some tabular data and maybe you want to add a little bit of noise to that tabular data so it's harder to overfit, but you don't want to add too much so that the sort of meaning in the data has been removed. So you don't want to apply any image augmentations that would potentially remove too much information so that, say, our classifier can't actually classify. You want to keep the actual information that you need to extract, or your classifier needs to extract. You want to keep that there. So it could be the case that if you're randomly resizing, downsample and upsample again, so you have the same image size, if that downsampling removes too much information, it might be detrimental to the training of your model. Right? You have posterize, solarize, where we're changing the color and the amount of actual pixel values in the image, so on and so forth. So we'll skip that for now. I just wanted to have a look. I'll point out here, random horizontal flips. This is one of the transforms we're using. That's just simply flipping. So the picture to us looks very, very similar. It's just flipped. But again, the important fact is that the pixel values, the exact pixel values are different. The content remains the same. The same with vertical flipping. Okay. So hopefully you got an idea of why we'd use data augmentation. We're sort of virtually expanding our data set to have more images. And we do this at training time. You can do it as a pre-processing step, but it's not very, I guess, efficient, because you could be saving the same image multiple times just with different augmentations. So what we tend to do is we tend to save the sort of raw data, the raw images, and then we apply some augmentation, some transform to the image once we've loaded it. So as we've kind of seen before, these transforms are applied in that get item function of our data set. So as we've loaded them, and as that get item function returns them, it will then apply the transform. But you could, before you start training, run through the entire data set, make copies with all these augmentations so that you don't have to do it at training time, to save some, save some speed when you're training. Okay. So the two we're going to have a look at is just random rotation and random horizontal flipping. So random rotation is just going to pick a value. This degrees here just defines the max plus or minus that the image will rotate. And horizontal flip is just going to be flipping across the horizontal. You could also specify a p-value here, which is the probability that it will be flipped. It is by default 0.5, which we're just going to keep. Okay. The other one we're going to have a look at is Pytorch's auto augment, which I kind of zoomed past here. Where is it? So Pytorch's auto augment is basically a predefined set of transforms that are going to be applied to your image. So randomly applied. So auto augment this transform here. It is based on, or the set of transforms that they're going to be using is based on this paper here. And Pytorch has what they call 3 different policies. So each of these policies are just a different set of transforms with different parameters that they've defined. So they have 3 different policies. If you look at the auto augment policy, they have the ImageNet, Cipher10, and SVHN. And you can kind of see some of the different augmentations within each policy. We're going to use the default one, which is just ImageNet, which is sort of applicable for our STL10 dataset we're going to use. So that's very useful because it means that we don't have to think about the sort of transforms we should apply. It will automatically perform a set or perform transforms from a set of transforms. Okay. So like I said, the rest of the training code is very, very similar to what we had before. So we're not going to start from pre-trained weights, even though it says here, we're going to start from a random initialization, not using the pre-trained parameters. We're going to ignore this section for now, but it will be useful in the next video when we're looking at pre-training techniques. So our model trainer is very much the same as before. There's just one extra thing that we can pass it, and that is a learning rate scheduler. So a learning rate scheduler is basically, as we'll see, a way to dynamically change the learning rate during training. But before we get into why, what we're going to do is we're going to train a baseline or train our model with the default parameters, no augmentation, no anything. And we're going to see what we get. And then we're going to see if we can improve the performance by dropping the learning rate a little bit. But we're going to do this manually first. So we'll restart and run all, and we'll get back when training has finished. Okay, so we've finished training. And as expected, we have overfit quite a bit still. But one interesting thing to note is that as we've trained it for a while, we notice that there's this big spike in the loss here and a big drop in accuracy. Now, when exactly this happens varies a bit. Sometimes it happens earlier or later in training. And in the case of using such a big model on a small amount of data, we can have instabilities like this pop up. So if you've ever trained your model and you've got this sudden big spike in loss, sometimes it just comes back naturally, comes down naturally, but sometimes it doesn't recover. Sometimes it leads to more overfitting. So basically what's happened here is that our model is training, descending the gradients, and it's taken a step. And instead of decreasing the loss, it started increasing the loss. So a sort of analogy or a diagram that is often drawn, I'll see if I can draw it here, for what intuitively is going on is, if I imagine this is my loss landscape, it looks like this, and if we imagine our gradient descent is a ball rolling down the hill, as it often is, a ball here, we're going to descend the gradient, right? And how big a step we take is determined by our learning rate. So we take a step, maybe we've got some momentum, so we'll hop over this. Oh, and we'll maybe make those steps a bit bigger to illustrate my point. It's too big. We'll hop here. And like I said, our learning rate defines the size of this step, but what could potentially happen is we'll hopping down this gradient here, and maybe we take a step that's too big and we actually end up increasing our loss. So imagine this is our loss that we're trying to reduce, but potentially we take too big a step, we actually end up increasing our loss. Now, what looks like happened in our example with our training is it was a bit more dramatic. So you can imagine something that's, maybe something like this, like that, right? And we're hopping down our gradient, right? We hopped up to a set of parameters that's much larger, and we just expect to jump back down eventually because we've descended the gradient. But what can happen if our learning rate is still too large is that we can hop down here, but then we're just going to hop back up. We're going to hop back up, and we'll never actually converge to the real or to this minima here. So we'll just keep hopping back and forth, back and forth, back and forth, back and forth. So one thing we can do is at this point, what we can do is we can lower the learning rate. So we can make smaller steps and then hopefully actually converge to this point here. And then, maybe we'll bounce around in here, back and forth, but again, that's much better than before. So what I'm going to do this time is I'm only going to train for, say, 10 epochs, and we'll get back after 10 epochs. And what I'm going to do is I'm going to manually drop the learning rate that the optimizer has and continue training from then. So I'm going to delete the model that I've got currently. Again, the trainer will warn you if you've got a model that's already been saved. So I'm just going to train for 10 epochs now. Just going to quickly delete the model because I don't really need it. And we're going to train again for 10 epochs this time, and we'll get back when that's done. Okay, so that's finished the 10 epochs, and you can see it's kind of converged now. Again, it's going to overfit a bit because of the data set, but we'll get to that in a moment. But what we want to do now is we're going to manually drop the learning rate. So the learning rate parameter is stored in our optimizer. So we have our optimizer here, and what we need to do is we need to access the parameter groups called parameter groups. I can spell it. Parameter groups, and this is a list of a whole bunch of parameter groups, and we need the first one called params. So if you're interested, we're using an Atom optimizer, so we're going to have all of the momentum values for all the parameters of our model as well as the learning rates and the weight decay and everything else, but we want the learning rate, so it's a dictionary, so we have our learning rate here. So it's 10 to the negative 4, which is what we defined it as, and we can just overwrite this to set a new learning rate. So 2e negative 5, so 2 times 10 to the negative 5. So what's that? That's 5 times smaller. And I'm just going to enter and just verify. There we go. We've set our new learning rate, and I'm going to train this for another, we'll set it for another 20 epochs. So it's 30, 30, same as before. All right, let's keep going. All right, so that's done that 20 epochs. So it's saying 10 here, but that's just because we haven't changed the number of epoch parameter. Let me just change that. Plotting. Okay. So you can see we haven't had one of those big spikes in our training loss, right? No instability occurred, and we've just converged nicely. You can still see we have some little spikes there, so you could drop it even further, say after another 20 epoch or another 10 epochs. So you can stop those spikes as well, but I mean, it's overfit anyway, so it probably wouldn't have too much of an effect. But my point is that we want to potentially reduce the learning rate so that we can converge into a better local minima and, avoid maybe the loss going up, because it can happen. People seem to be quite surprised sometimes when you're training, the loss might start going up, the training loss might start going up, or either suddenly or slowly even. That's because your learning rate is just a bit too high, right? So we can manually set it like I have done here, but Pytorch also has what we call a learning rate scheduler. So what we did then was a sort of step learning rate scheduler where after a certain number of epochs, we've stepped the learning rate down. And like I said, you can do that multiple times. But Pytorch has a scheduler that will potentially, well, that could do that for you. So we're going to have a look at, where are we? Pytorch's learning rate schedulers. So where are we? You can see Pytorch has a large number of different types of schedulers. And I'm going to go through just at a high level, a few of them, and we're going to look at two of them in particular. Okay. So the first one called Step LR. So if I just uncomment this out, as I mentioned before, the only real difference between the model trainer from the previous section and this one is that we can set, where is it? A learning rate schedule. That's what we're doing here. So this first one, Step LR, documentation here, you can see that it decays the learning rate of each parameter group by gamma every step size epochs. So to translate, basically it'll take the current learning rate and it will multiply it by a fixed value every number of steps that you've defined, right? So the first thing we need to do is we need to pass it, where are we? Pass it the optimizer. So our model optimizer, step size and gamma. So step size is how many steps need to occur before we multiply our learning rate by gamma. So gamma is going to be less than 1. That means we're going to decay that. So step LR, as you'll see in this little example here, is designed to be stepped once an epoch. And as you'll see, some of the learning rate schedulers are designed to be stepped once an iteration. So every forward pass, back pass, update step, we're going to reduce the learning rate by a little bit. But step LR, step learning rate, is kind of like a crude learning rate reduction. So a very large-ish step every epoch, right? And that's how I've designed the trainer to work as well. Currently, the step learning rate scheduler step is in the run training method, which does the epochs over the training and evaluation. So we'll do a whole epoch of training and then run the step. I'll show you in a bit how we can modify this so that it runs every iteration, not every epoch, but the two learning rate schedulers I've got are designed to be stepped once an epoch. So this step will just apply that step decay of the learning rate. Now with something like this step LR, you've got to be careful about the gamma parameters that you pick, as well as the step size. Effectively what's happening here is that the learning rate will decay, it's as an exponentially decay, right? So we've got 0.95 here, and I'm just using Wolfram Alpha for this, and we have 30 epochs. If I run this, we should see how our learning rate should decay over those 30 epochs. This will be times the initial learning rate, which is, like I said, 10 to the negative 4. But you can see how it's going to decay. So I've picked these values, this value of gamma, so it doesn't decay too quickly. If I did something like even just 0.9 instead of 0.95, it might decay too quickly. And if you do something even smaller, then it might decay very quickly. You don't want it to decay too quickly, and you end up spending a lot of the last epochs not actually updating your model very much. So make sure you pick a good value for that, as well as the step size. Because we're stepping once an epoch, it's going to kind of look like a staircase, not this smooth graph, but hopefully you get the point. Okay, the other one we're going to look at is very similar, but it's called cosine annealing learning rate. They say it's based off of this stochastic gradient descent with warm restarts, but this actual implementation does not have the warm restarts in it, so that's important to know. Effectively, this is just a cosine scaling of the learning rate. So instead of step size and number of steps, what you define is the maximum number of steps, right? So here, so Tmax, in my case, it's going to be epochs because I'm going to step once an epoch. But this one, unlike step LR, you can do steps per iteration. You're just going to have to change this to the maximum number of iterations, which is going to be the number of epochs multiplied by the size of your data set. But we'll get to how you can do that. I'll show you how you do that a bit later on. Right. So cosine annealing is, like I said, we'll pull up a graph of this really quickly. If you have a look at the paper, we're effectively cosine decaying the learning rate. Well, I don't know if they have a plot in here. Yeah, I'll just draw it out again. Okay. So instead of doing that sort of exponential decay, what we're doing is we're using a cosine. Well, if you can imagine, a sine function or cosine function, it's basically, can't draw straight from here to here. This section of the cosine, right, that's going to be 1, and we imagine this is going to be 0. So we decay from the start learning rate down to 0 in this smooth cosine function, right? And you can apply this every iteration instead of every epoch to decay the learning rate, but we're going to do it every epoch. So it's a bit different. Step LR just kept multiplying the learning rate by gamma and gamma and gamma and gamma and gamma and gamma forever for as many steps. But cosine annealing, you have to say, this is how many steps I will perform total, so that it knows where this 0 point is, and will decay the learning rate for you, right? You're going to get, I think you get an error if you try and step past that. Okay, so that's our cosine. Going to quickly go through a couple more, or just point them out in case you're interested. Cyclic learning rate is basically a method of cycling the learning rate. So instead of decaying it smoothly, you actually decay it and then bring it back up, and decay it and bring it back up in a cyclic fashion. One issue with these sort of constant decaying learning rate schedulers is that if you want to start training it again, well, then you might have a problem if you've decayed your learning rate down to near 0, because you might not want to start it from the same learning rate again, because you're not going to actually move it very far. So you probably have to increase the learning rate, and increasing the learning rate might make you take a big step out of that local minima again, and so you're going to have problems. The cyclic learning rate still has the benefit of it does help you achieve a better local minima, but because of its cyclic fashion, if you want to start training again, well, you just pick up where you left off in that cycle and you can keep going. The other type of learning rate scheduler is what I'd call a metric-based learning rate scheduler, such as this reduced learning rate on plateau, where what you do is you provide a metric with which the learning rate will decay the learning rate if a certain criteria is met. So the little example they've got here is the validation loss. You could use validation accuracy. You can use any metric really, and you define a threshold and a threshold mode. So define a threshold and say, once the value of this parameter, this metric, has dropped or increased past this threshold, then step the learning rate down. So, or once it hasn't, potentially. For example, let's say your validation accuracy has converged, only step the learning rate once it's converged, right? Or your training loss has converged, then you can step the learning rate once the training loss has converged. So it's a bit of a different way. Instead of just decaying the learning rate on its own, you're paying attention to some metric and decaying the learning rate once that metric has met some criteria. So that's just the last type of learning rate scheduler that I wanted to point out. Okay, so we've covered a lot. Let's get into seeing what the effects of these different training techniques are. So the first thing I'm going to do, I'm going to keep the step LR learning rate schedule and we'll change this back to 30 epochs. So I'm going to copy this test accuracy. Comment here, I'm going to say this is the baseline, 49.35. So not a great test accuracy, but that's going to be my baseline. So we're going to run it again, and let's start using some of these transforms. So the first thing I'm going to do is random rotate and random horizontal flip. Okay, so let's train with those and see how we go. All right, we finished training and we can see our validation accuracy, our highest validation accuracy is now 60%. And we go through our plots here, you can see our training losses converged much slower this time. And the training accuracy also has converged much slower. And our accuracy got much higher, and our test accuracy now is much higher. We've got over a 10% increase in accuracy just from those two augmentations, plus the learning rate scheduler would have helped a little bit as well to converge nicely. So you can see the noise, the variance of our training loss getting smaller and smaller and smaller over time. The learning rate scheduler would have helped with that as well. So have a look at our images here. You can't really tell the horizontal flipping because they look the same, but you can see the rotations in there. So just by flipping and rotating and the learning rate schedule as well, we have got an increase in 10% accuracy. So that should kind of tell you that data is our problem. We don't have enough data. One other thing I just want to point out, I realized I forgot to mention, is that I'm only applying these transforms to the training set. They're also applied to the validation set because of the way I've split them, but maybe you don't want to apply them to the validation set. But the test set is getting the transform without the augmentations. So it's like comparing against the raw test baseline. Okay, so I'm going to copy this one down as well, 60.9%. So to org plus step LR. There we go. So let's now have a look at using the auto augment. So let's comment these ones out, just use auto augment on its own and run it for the same amount of time. Okay. All right, so we finished training that. We can see our highest validation accuracy was 56.6%, so a little lower. However, our test accuracy is almost the same at 59.19%. So if we have a look at our augmented images here, you can see that this auto augment, or this policy that we're using, which was the ImageNet policy, does a lot with color. And again, this is for a model that was trained on ImageNet, which has a lot of data. We don't have a lot of data in this case, so maybe it's not as applicable. As you can see, it does a lot with the color and the saturation of the image. It does some rotation, but a lot less than what we do. We do a rotation for every, or we were doing a rotation for every image. A side note as well, if you don't want that to happen, for a lot of these transforms that don't have a probability value, you can use this random apply to wrap around a list of transforms so that they are only sometimes applied. So that's just a side note. But you can see that, again, it seems to help get a 59.19% accuracy. So I'll add that to the list. And what we'll do is we'll then train with both. Let's see what happens when we train with both. So bear with me, and we'll train with both. All right, so we finished training that as well. Have a look. We can see our auto augment and also our rotations. Our flips is there as well. Our augmented images. Because our validation accuracy was 59%. You can see our training loss hasn't actually yet converged. So we can potentially still train this for a bit longer. But you can see, yeah, maybe our validation accuracy could go up a bit higher as well. You can see our training accuracy hasn't actually converged yet as well. So it hasn't quite overfit as badly as before. And you can see our test accuracy is now 64.91% accurate. So now we've got an even better test accuracy. So that's good news. One thing that I want to talk about or mention is that I've had comments from students who maybe are a bit confused about how these augmentation and even other regularization techniques seem to make it harder for our model to learn. Right, our training loss is now a lot worse. So even though they sort of understand the problem of overfitting, but these augmentations have sort of made our training loss worse. And how do these augmentations or these regularization techniques help improve our model if they're making the training loss worse? Well, I counter that usually with our validation and our test accuracies won't get any better if the training loss has converged. The training loss is what our model is trying to optimize, what it's trying to reduce, right? And the derivative of our loss with respect to our parameters, so the gradients from the loss, right, will also converge as our training loss converges to zero. As our training loss gets closer to zero, the gradients will get closer to zero, not if it converges. So if our training loss goes very, very close to zero, then our model will basically stop updating, and no matter how long we train it after that, the validation and test accuracies are not going to get any better. So a lot of these regularization techniques, or just adding more data, not just data augmentation, what that does is that keeps our model training for longer. It keeps that loss from converging to zero for longer so that our model is always updating, right? And again, we want to do that in a way so that if the training loss does converge close to zero, then the test and validation accuracies are better. If we were to just add a lot of random noise to the input images, then sure, the training loss won't converge close to zero, but that's not actually helping testing and validation. So these data augmentation techniques are basically ways of making it harder for our model to memorize the data, helping regularize it, help stop overfitting, but also in a way that will help test and validation performance if the model actually does learn and reduce its loss. Okay, so 64.19%, that's the best of all of them. The last thing maybe we'll do is we'll just try that last cosine annealing instead of this step LR. I'm not too sure how much better it will be, but we can have a go at that. And then we'll have a look at how we can change how we do this stepping so that's every iteration and not just every epoch. So we'll restart again with our new cosine annealing learning rate. And we'll see what happens. All right, so we finished training, validation accuracy 60%. You can see our training loss is still probably hasn't converged as much or converged yet, but we can see that our test accuracy is now 66.03%. So we've got about an extra 1% really on top of the previous one. So got a little boost from using a slightly different learning rate scheduler. And we can have a look at our learning rate and you can see it's now converged to zero, right? Because we've set the max number of steps to number of epochs, we've reached it. And so our learning rate is now zero. So this is what I was kind of saying. If you wanted to continue training from here, well, it might be a bit difficult. It might not be too much of a problem. You'll get a bit of a increase in the loss, but it'll probably converge again. The last thing I wanted to talk about though is let's modify the code a bit so that we're taking a step per iteration with our cosine annealing learning rate schedule. So in our trainer, all we need to do, not too complicated, I'm just going to cut this from here and we're going to put it inside our training loop. So now every iteration, we're going to take a step of our learning rate schedule. What this means though, is that we need a lot more. We need to tell the actual scheduler there's going to be a lot more steps. So I'm going to just define another variable here, which is going to be the number of steps. That's going to be the number of epochs multiplied by the iterations per epoch. And we can get that very easily from the actual model trainer and its train loader. If you take the length of the train loader, you will actually get the number of iterations per epoch. Just set that like that. Look at the total number of steps. See, there's going to be 2,130 total steps, which makes sense. We've got 71 iterations per epoch and 30 epochs. So we'll retrain again with this. Hopefully that update made sense. Just moving this into our training loop and changing the total number of steps. So let's train this. All right, so training's done. Validation accuracy is a bit higher, but the test accuracy is pretty much the same. That's okay. The very last thing I want to try though is training a bit longer. You can see our validation accuracy hasn't quite converged yet. Same with our training loss. So the very last thing I'm going to try is training for a bit longer, or maybe twice as long. So we've gone from a case where our training loss was converging very quickly, and our training accuracy was converging very quickly, and our validation accuracy was converging very quickly, to a case now where even after 30 epochs, we're still converging and we're still improving. So you can see how making some changes means that what you may have thought was, too long to train for, 30 epochs, is now not enough. So you can see how we have to constantly be changing all these different parameters. So, we've got a little summary here, how we've iteratively improved performance, and this is what you would do. You change all these parameters, maybe even batch size, to get a better performance. So we'll double the number of epochs now, and we'll train again. All right, so that's done. Our 60 epochs is over, and we've got a 65% validation accuracy. So done even better. Our test accuracy is almost hitting 70% accuracy, 69.62% accurate. So you can see how we've gone from, like I said, this, for the initial set of parameters that we were training with, something that was converging very early on, wasn't improving, but by adding these augmentations and these learning rate schedules, we have improved our performance quite a lot, going from what was 49% accurate to 69% accurate. So an extra 20% improvement in accuracy just by changing how we're training our model, just from changing our training techniques for our model. And we haven't even used any pre-trained parameters. If we did, I'd imagine we get an even better accuracy, even better than just the baseline using the pre-trained parameters. So that's basically what this video is about, how we can improve performance just by changing the parameters of our training, right? So hopefully you got something out of this video, or at least I've pointed you in the right direction of where to look for our learning rate schedules, where to look for our transforms and what we can do, and what you should make sure you're, doing, making sure you're not doing augmentations that don't really make sense or might remove the information. But if you enjoyed this video, remember to subscribe and like, and I'll catch you in the next video where we will be looking at how we can utilize additional data or unlabeled data to improve our accuracy even further. So our STL10 dataset, as I mentioned in the previous video, has 100,000 unlabeled images. These are images with no labels. And so we'll see how we can use unsupervised learning techniques to use images without labels to pre-train our model to improve our supervised learning even more. So I'll catch you in the next one.